All right, we are going to talk about some applications of exponential equations, and their main application is to growth and decay models. They're actually kind of simple. So you start out, here's your function. It could also be called f of t, where you've got a, r, and t. This stuff inside, 1 plus r is called the growth factor. 1 minus r down here is called the decay factor. And then the rest of it is defined as this. Y is the final amount, A is the initial amount, R is the percent increase or decrease, and then you do have to put that as a decimal. This right here, this R is actually called the growth or decay rate. Makes sense, right? And then T is the number of years. So over here, looking at these examples, y equals 4 parentheses 0.59 to the t. Now, how could we determine whether or not it was growth or decay? Well, if you think about the growth model, the growth factor is 1 plus r. The decay factor is 1 minus r. So if I have 0.59 here, could that have been 1 plus some rate number? No, the only way you can get 0.59 is if you subtracted a number from 1. So this one's got to be decay. This one is more than 1, so it's going to be a growth. And that's the key. Is your growth factor will be more than 1. And if it is a decay factor, it'll be between 0 and 1. I should write it in words. Between 0 and 1. Okay, now initial amount, again, initial amount is that A, this number out in front. So in our case here it is 4. Here it is 230. All right, growth or decay factor. That is the thing inside the parentheses. So growth or decay factor here is 0.59. And the growth factor here is the 1.2. Okay, now growth or decay rate, you have to figure out what R is. So in this case, what happened was we took 1 minus R and got 0.59. So the easiest way to find that growth or decay rate is then to switch those guys. Ooh, what happened there? Oh, sorry about that. I had to go make me some dog pie. Just kidding. Okay, so the best way to find R here is to take 1 minus the 0.59. So we're basically just swapping places. They're wagging their tail. They're going to bark again. So here the R would be 0.41 or 41%. Now, similarly, over here on the growth side, we took 1 plus R equaled 1.2. So this time, if you take the 1.2 and you, why do these weird things keep showing up here? Giggle. Sorry, can't find my relacer. Can't find my relacer. Oh my gosh, I gotta pause first. Okay. Likewise for the growth, it was 1 plus R equaled 1.2. Oh my lord, the exact same thing happened. Why is this happening to me? 1.2. That's a point. Whatever. So to find R, now it's just a matter of taking 1.2, the growth factor, and subtracting the 1 back away from it. So in this case, R is 0.2 or 20%. Okay, let's start doing some of these. Here's one example. The value of a mountain bike can be approximated by the model. So here's our exponential growth or decay model. T is the number of years since the bike was new. Tell whether the model represents a growth or decay model. Well, you look inside here. Since the growth factor, this number inside here, is less than 1, it's going to be exponential decay. And the growth and decay factor, like I said, was 0.75. The annual percent or decrease, growth or decay rate, in the value of the bike. If my growth factor is 0.75, then my percent increase or decrease is 1 minus 0.75, which is 0.25 or 25%. Okay, what will the value of the bike be after 3 years? Well, now they're giving us a T. I don't know what is going on with this thing. It is driving me nuts. T equals 3. Bazinga. T equals 3. So if we plug it into our formula up here, y is going to equal 200, parentheses, 0.7. Oh my Lord, what is happening here? I laugh because I have to. I'm sorry, this video is going to be half of me giggling. All right, I'm just going to write really careful and slow. It's to the t power, but the t is actually 3 here. So if you calculate that out, you would get, I get about 84.38, and that's the value in dollars. So $84.38 is the value left of the bike. Then this one says when. When will the bike be? When will the value of the bike be $50? So now we're trying to find T. And this is our Y, or f of t, or whatever the function uses. Y, f of t, it doesn't matter. So I'm going to fill in the pieces I know again. I'm going to go 50 for Y. The rest is the same, except now, instead of 0.75 to the 3, it's going to be to the t. Now we have to solve using our exponential and log conversions. So I'm going to get rid of this 200. So I end up with 1/4 or 0.25 equals 0.75 to the t. Okay, in order to solve that, we need to convert to a log. I prefer to write my powers on the left side. So we have log, base is 0.75, of 0.25 equals t. So t is approximately about 4.8 years. Okay, basic growth or decay model. Let's try this one. Fred buys a car for $25,000. The car depreciates, that's a key word you've got to learn, at a rate of 15% per year. Tell whether the model represents exponential growth or decay. This word right here, depreciates, means the value gets lower and lower and lower, which would mean it would be decay. This word depreciates means decay. Decreases, depreciates, decay, all of those are going to mean the same thing. This time we need to write a function that represents the value of the car, y, with t as the number of years since the car was purchased. All right, so our basic exponential decay model looks like this. Y equals a times 1 minus r to the t. A is our initial value. Looks like up here in the problem it gives us that, right? It says it starts for 25,000. Okay, now we're going to go to 1 minus r. It also gives us r though, 15%, which will be 0.15. Okay, and then we've got to the t power. Now to finish out our answer, we would write 25,000, parentheses, 0.85. I just took the 1 minus 0.5 inside and combined them together. And that's to the t value, t power. All right, C says, what will the value of the car be, so y, after 6 years? That's a t. Y equals 25,000, 0.85 to the 6th power, which is about, looks like 9,428.74. Wow, 6 years is not worth much, huh? 15% depreciate rate is really high. Okay, when will the value of the car be 8,000? Okay, that becomes a y because it was given to us. We know that we've got to find the t because it says when, not one, it says when. When will the car be 8,000? That's our y. So just like the previous problem, I'm going to plug in 8,000 for y. Still have 25,000 for the initial amount, 0.85, and then we've got t up here in the power. Divide by 25,000. That's 0.32 equals 0.85 to the t. And we got to convert to that log. Log base 0.85. You see why it's, I prefer to write the power on the left because it would get really confusing right there if I had written log base 0.32 of 0.85 because you're used to it being on the left side. So I just always switch so I don't make that mistake. Okay, we've got log. The base is 0.85 of 0.32. That's t. So t is approximately, I get 7.01, so we're just going to say about 7 years, approximately. Okay, next one we're going to talk about is one called half-life. It's a specific kind of decay. I'm going to pause right here and switch to a new video though.